So, very good evening to everyone, and welcome to the NPTEL's 8th live interactive session on the course Mechanical Behavior of Materials, Part 1. The course instructor for this course are Dr. Shashank Sekhar and Dr. Sudhanshu Sekhar Singh from the Department of Material Science and Engineering at IIT Kanpur. And myself, I am a myself, Shivam Jaiswal. I am a research scholar in the Department of Material Science and Engineering at IIT Kanpur. So in this live interactive session, we will be going to solve some concept related questions which are related to your weekly content and which will in turn will help you to solve your weekly assignment. So in this live interactive session, today we will quickly recapitulate what are the things that has been covered in the week 8, followed by some concept related question, and if the time permits, we'll try to discuss the assignment 8. Okay, so let's begin. So coming to the recapitulation of the week 8. So week 8 we begin with the concept known as the critical result shear stress. So what is critical result shear stress? It is the minimum value of tau r that must be applied for a dislocations. So consider we have a material and we have applied a stress to its axis. Okay, if the dislocation needs to be moved, so it should satisfy the condition that it should apply the minimum tau r. Okay, so so when we apply, the shear stress will be generated in the material, and if that shear stress is greater than the critical result shear stress, then the definitely our dislocation will move. So let's consider material. Okay. Let's say this is our material, and here at some angle, one slip plane is oriented. Okay. So let's say the normal. Sorry, guys. The normal of this slip plane is, let's say, this is N, and it is loaded in the loading direction or on this face. Okay, with the load P or stress sigma. Okay, and the angle between the loading axis and normal of slip plane, let's say it's phi, and this is the slip direction. Okay, so the angle between, I will write it is SD. So the angle between the slip direction and that of the loading axis, let's say it is lambda. Okay, and let's say this is my area A, and this is my area of slip plane is A dash. Okay, so let me write down phi the angle between normal to the slip plane and loading axis. Similarly, lambda is the angle between the slip direction and loading axis. Okay. So if we find out the component of the load that is acting on slip plane in the slip direction, so component of load acting on the slip plane in slip direction. Okay, so let's say here the that is load is acting, that is the P dash. So this P dash is nothing but a P cos lambda. Okay, if we resolve that load P, so in the direction that of the slip direction, so it will come out to be P cos lambda. Okay, and if we do similar with the area, so the area is nothing but A dash cos phi equal to A. Okay, so now if we find out the shear stress acting on that slip plane or the result shear stress, so shear stress, that is tau r, is nothing but the load acting on the slip plane divided by area of slip plane. Okay, so that is A dash. So if we put the value, we'll get something P cos lambda divided by A cos phi. So finally we'll get tau r is equal to P by A cos lambda into cos phi. So this P by A is nothing but the stress, normal stress, that is tau r is equal to sigma cos lambda dot cos phi. So this is the equation that we got for the result shear stress. Okay, so now after this we have discussed that the tau r, that is the result shear stress, that and the n, that is normal to the plane, and the p, that is the load acting, need not to be lie on the slave plane. Okay, so it means the phi plus lambda need not to be 90 degree. Okay, and also similarly the lambda need not to be 90 degree. So the result shear stress normal to the slip plane and loading axis need not to lie on same plane. So what does it imply? That is phi plus lambda need not to be 90 degree. That is need not to be 90 degree. Okay, so these are the things we have seen. Then we have compared that this is the critical result shear stress, that is the minimum value of the result shear stress that must be applied for dislocations to move, is nothing but a single crystal equivalent of that of the yield strain. So tau CRSS is single crystal equivalent of yield strength. Okay, so after that we have seen the relation between the critical result shear stress and the pulse level shear stress, or also we can see that the similarity between them. So relation between tau CRSS and the pulse number, that is tau pm. So both of these, that is the critical result shear stress tau CRSS and the pulse Nabarro stress, that is the tau PN, represent the minimum shear stress that is required to overcome the lattice resistance. Okay, and if we see the tau PN is basically the theoretical value that is needed, and whereas the tau CRSS is the experimental one. Okay, and while calculating the tau PN, the temperature that we have considered is at the 0 Kelvin, whereas in the case of the tau CRSS, uh, the temperature is nothing but the temperature present at the time of experimentation. Okay, so let me write down some few points. And tau PN is defined as at 0 Kelvin, whereas tau CRSS is the experimental quantity and it is obtained for a given temperature. So tau CRSS can change with the temperature and as well as with the material composition. So as I was told that the tau CRSS is experimental values. Okay, so if I change the temperature, it will change. Similarly, with the composition, it will change. But the result shear stress, it is not the property of a material. Okay, it will change with the geometry as well as the orientation of the slip plane and some uh, like what we can say the with the crystal structure as well. So this is not a fundamental property of material, whereas tau CRSS, that is the critical resolve shear stress, is the property. Okay. So the equation for tau CRSS that we got is nothing but means that is the tau r equal to sigma cos phi into cos lambda. Okay. Then after that we have seen the what is hard orientation and soft orientation. So as in the equation of the result shear stress, that is the cos phi and cos lambda, that is the slip plane is oriented at some angle, and the slip direction will be making some angle with the loading axis. So what will happen? There are some planes inside a material, or so that will experience a smoother flow. Okay, what we can say in other words that so they will deform easily, whereas some planes are there that will not deform easily. Means that are somewhat difficult to sleep. Okay, so that we have seen in the term of known as Schmidt factor. So the tau r is nothing but sigma cos lambda into cos phi. So this product of cos lambda and cos phi is known as Schmidt's factor and denoted by letter m. So m is equal to cos lambda dot cos phi. So if I need to move a dislocation, so what should the minimum state that should I apply, we can get from here. So it is nothing but sigma equal to tau r by m. Okay. So if we want to lower the stresses required for easy movement, so our value of the Schmidt factor, that is m, should be higher, and it is possible when the phi and phi and lambda are small, as this both are nothing but the cos lambda and cos phi, and its value will be higher when the phi and lambda will be smaller. So for maximizing factor, angle phi and lambda must be minimum. Okay, so after this we have seen one experimental result, that is y-axis represent the sigma, and on x-axis we have varied the phi from 90 degree to 0 degree. Okay, so before that we will see how they have derived. So that is, if we want to find out the absolute minimum of the sigma, then the result shear stress and normal shear stress and the normal of the slip plane must lie on the same plane. That is, phi plus lambda should be equal to 90 degree. So let me write down. It is that is phi plus lambda equal to 90 degree. Okay. So we know m is given by cos lambda into cos phi. So if I put the value of lambda in terms of cos phi, so what I will get? M is equal to cos 90 minus lambda into cos lambda. Okay. So if I simplify it, I will get m is equal to 1 by 2 sine 2 by lambda. So if I need to increase the value of m, then it should be it is same as the increasing the value of sine 2 lambda. So in sine 2 lambda, that is the 2 lambda should be maximum, and it is how much maximum it is possible? It is 90 degree. That is, sine will be maximum at 90 degree. So 2 lambda equal to 90 degree. Therefore, lambda equal to 45 degree and phi is also 45 degree. So in the experimental results, what they have seen, 45 degree, the stress is decreasing, and it at angle of 45 degree, it is minimum. Okay, so if we plot the value of m, that is the Schmidt factor, with the same, so what we will get? The Schmidt factor will be higher here at an angle of 45 degree. So if we see here, the orientation, that is 0 and 90 degree, here the stress required is more. So these are the hard orientation. Whereas if we see the some region close to that 45 degree, so the stress required is minimum for the yielding. So we can see that say that these are the softer orientations. So, orientation close to 0 degree or 90 degree or hard orientation, whereas those close to 45 degree are soft orientation. As low stress is required for yielding. Okay, so generally we can see that in any given slip system, the planes which are oriented at an angle of or near to same the or close to that of 45 degree will yield first or will slip first. Okay. So these are the things that we have discussed regarding the critical result shear stress and Schmidt factor, and what is the effect of angle, that is the phi and lambda. So after this, we have seen the concept that is the interaction between dislocation. So we have seen the interaction between the dislocations. So suppose in material, if more than one dislocation is present, so the stress field of dislocation one will be applying some or exerting some force on the dislocation two. So this will change the how much external force will be needed for a dislocation to overcome a lattice resistance will change because of the interaction of these two dislocations stress field. Okay, so suppose let's consider here I have a one dislocation. Okay, and this is dislocation one, and here I have a dislocation two. The forces will be exerting Fx, Fy, Fz. Okay, so or we can have a jungle of a dislocation and it will exert a force on a single dislocation. That is also possible. So let's say okay, so this can also affect the exert the dislocation. So what we are saying that So when we load the material, so then the dislocation density in the material is increases, so that the this dislocation will exert a more force on the our second dislocation, and that will result in the increase in the stress required for the means that will require the excessive stress to overcome a internal resistance. So we can say that this is the origin of our strain hardening or the strengthening, we can say. So as we apply more and more load, so for the deformation it will require more and more load. Okay. So this also I can write down. Okay. So these are the things we have discussed in the interaction between dislocation. Then we have seen the Pitch-Kohler equation. So this equation gives the force per unit length at any point of time acting on the dislocation. So let me write down. So Pitch-Kohler equation. So it is given by sigma of 1 into B2, that is the Burgess vector of 2 second dislocation and cross product of its sense vector or line vector. So here in this equation the F is nothing but force per unit length at any point on dislocation 2. Okay. So this sigma 1 is nothing but the stress field of dislocation 1, or in simple word we can say this is the same stress that will be experienced by the dislocation 2. So stress experienced by dislocation 2. Okay. And this is B2 is nothing but the Burgess vector for dislocation 2. Burgess vector for dislocation 2, and this is that epsilon is the line vector for dislocation 2. Okay. So we can write this equation as that sigma I can write sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz into sigma zx, sigma zy, sigma zz into the Burgess vector, that is bx, by and bz, and its cross product with the sense vector, that is epsilon x, zeta x, zeta y and zeta z. Okay, so we can solve this cross product, like if it is A cross B, then we have here I, J, K, A1, A2, A3, B1, B2, B3. Okay, so if we solve this equation, So we will get a forces, that is Fx, Fy and Fz. So this will be the glide force and this will be the climb force. So these are the things we have seen in the pitch Kohler equation. So then after this we went to see the interaction between the dislocation. Okay. So the first case that we have seen, that is the interaction between two positive edge dislocation. Between dislocation. The first case that we have seen is the interaction between two positive edge dislocations. So case one is so let's say this is my dislocation 1 and this is my dislocation. Let's say this is my dislocation 2. So let's say this is the distance x and this distance is y. So if we apply the pitch Kohler equation, so what we will get, that is F bar equal to sigma yx Burgess vector of second and Sense vector of second. Similarly, here we will get, that is the climb force, that is F1 sigma xx b2x epsilon z of 2, and the third component it will come out to be 0. So this is our Fx, or we can say glide force. Fy is climb force. Okay, so if we put the value and if we consider both the dislocation have the same Burgess vector, so we can write at the Fx, that is if we consider both are the positive edge dislocation, or if we consider one is the positive and one is the negative, so we can write Fx as plus minus GB square 2 pi 1 minus mu into x square minus y square divided by x square plus y square by 2. Okay, so this is the equation that we got. Okay, so if we consider that both are the dislocations are moving on the same glide plane, so what will, so in this equation the y will become 0, so we only left with the equation that is GB square upon 2 pi 1 minus mu into 1 by x. So okay, both on same glide plane, that is y equal to 0. So Fx equal to plus minus GB square 2 pi 1 minus nu into 1 by x. Okay, so here if we can see that if the both the edge dislocations are the positive in nature, then they will repel each other. Okay, and if they are of the opposite nature, so what will do? They will attract each other and get annihilated. Okay, the similar thing we have proven with the concept of energy of dislocation. Okay, so if we consider that the both the dislocation are of the same nature, so we can see that for single dislocation, the total energy will be alpha gb square plus alpha gb square. It comes out to be 2 alpha gb square. Okay, but if we consider they are very close to each other, then the net Burgers vector will comes to be 2b. So if we consider it's energetically, so it comes out to be 4 gb square. So which is energetically not favorable. So it will repel each other. Whereas if we consider the dislocation with that of the opposite nature, so the net Burgers vector will be 0 and the energy will be 0. So which is less than the alpha 2b gb square. So it is energetically favorable. So the in short, the with the same nature it will repel, and with the dislocation with the opposite nature it will try to attract and annihilate. And so this is the condition when the both of the dislocations are on the same glide plane. Okay, so suppose if it is not, means both the dislocations are not on the same glide plane. Okay, so if we consider in that case, and if we consider both have the same nature, so let's say both have a positive edge dislocation. So in this, let's consider this condition. Okay, they are at some angle. They are making some angle with the first dislocation. Okay, so if we represent and the values of y in terms of x, so we can plot a curve. So let me. Okay, so this is x. Let's say this is our force. Okay, and if we represent the values of y in terms of x, this is y, 2y, 3y, 4y, minus y, minus 2y, minus 3y, minus 4y. Okay, so if I consider the both of the same nature, okay, so at x equal to 0, the force will be 0. Similarly, at y equal to 0, it is also 0, or at y equal to minus 1, it is also 0. And in between, it will vary. So how it will vary? So it will vary something like this. Okay, so here we can see that if both of the same sign, like so, both of the same sign. Okay, so if two dislocations are on top of each other, so if it try to move this side, okay, so this force will try to push it back to its original position. So this position is the stable equilibrium. And these positions are unstable equilibrium. So this is the case of for both with the same sign. Now, if we consider both are with the different sign, so similar type of curve will get, but it is in the inverted. So here we'll get something like this. We'll get a curve something like this. Okay, and if we consider that is both of opposite sign. Okay, so here we can see that if it is try to move from this point towards the left or towards the right, so it will again push it back to the same position. So we can say that the dislocation with the opposite signs are stable at an angle of 45 degrees. So this is their stable equilibrium, and this position is unstable equilibrium. Okay. So these are the things we have seen in the dislocation interaction between the two edge dislocations. Okay, so let me make it boundary so that you will not get confused. This is for this, and for this it is so here you can see this is both opposite sign, and this is so this is both of the same sign. Okay, so after this we have seen the second case, that is the interaction between the screw dislocation. Okay, and that two are parallel to each other. So, case 2, interaction between two screw dislocation, and that two are parallel. Okay. So in this case, the force is given by Fx GB1 B2 upon 2 pi into x upon x square plus y square. Okay, if both are of the same sign, then the Fx will be greater than 0. That is, it will try to repel each other. And if it is opposite nature, means one is the opposite nature, so the Fx will come out to be less than 0. So they will try to attract each other. So let me write down with same sign Fx greater than 0, it will repel. Opposite sign Fx will be less than 0, and it will try to attract. Okay, so this was the second case, and then we have seen the third case, that is the interaction between one edge and one screw dislocation, and both are parallel. So case case 3. Interaction between edge and screw dislocation. Screw both are parallel. So what will happen in this case? Any guesses? Any guesses, guys? So in this case, the forces exerting will be 0. So no force will be acting on a screw dislocation due to edge dislocation or vice versa. So okay. So these are the different cases of interaction of dislocation. So after this, we have seen the concept of image force. So image force also we can call it as imaginary force. So let's say we have a bulk material and there is some dislocation near to the surface. Okay, so because there is some relaxation or near the surface, so what will happen? This dislocation will try to move out. Okay, so it means some type of force is exerting on that dislocation. Okay, so we need to evaluate, calculate that force. Means how what force is being applied on that dislocation so that it is moving out. So to answer these questions, we will be using the concept of image force. So what they have considered, let's say, okay. Let's say this is the bulk material, and here, okay, and here we have a dislocation near the surface. Okay, at a distance of d. Okay, so now what we will do? So we will put one more dislocation which is of the opposite in nature. Okay, means if it is means both this dislocation will be opposite and it will have the Burgess vector magnitude same as that of the original one. So let's here I am putting one. Let's say this is a D. This is my imaginary dislocation. And it has the same Burgess magnitude. Okay. So what will happen? This dislocation is applying some force so that the dislocation inside the material is coming out, and that is same as that of the attractive force. Okay. So, and this force is only experienced by the dislocation near to the surface, means some few nanometer up to some few nanometer level. So now here we can easily calculate, as these are the two dislocation opposite in nature and exerting forces. So simply if you apply the pitch Kohler equation, we'll get the equation, that is Fx if it is the edge dislocation. So the equation for edge dislocation is what is gb square upon 2 pi 1 minus mu gb square upon 2 gb square upon 2 pi 1 minus mu x into x square minus y square divided by x square plus y square whole square. So if in this equation both the dislocations are lying on the same plane, it means y equal to 0 and x is equivalent to the d. So if we put, we will get the equation something like this: gb square 4 pi 1 minus nu into 1 by d. So this is for h dislocation. Okay, and the similarly for the screw dislocation, what will it will be minus gb square upon 4 pi into 1 by d. This is for screw dislocation. Okay. So when does the dislocations will move out of the surface? So it should satisfy any criteria, then only it will come out from that from the means near to the surface. Okay. So any guesses? So if the Fx is greater than the lattice resistance, that dislocation will move. So, and these are the things we have covered in the last week concept, and in the end we have seen the partial dislocations, how they are found in the FCC, so how they create a stacking fault, and how the partial dislocations are being represented. So whether the formation of the partial dislocation is energetically feasible or not, and what are the conditions that it should follow, that it should be energetically favorable, and it should have the same plane, and it should satisfy the vector addition. So these are the different things we have seen the regarding the partial dislocation. Also we have seen how these partial dislocations are represented in the Thomson's tetrahedron. So these are the things we have covered in the last week content. So any doubt till now? If there, please ask. Otherwise, we'll move we'll move towards solving the problems. So any doubt, guys, till this point? Okay, so we'll move towards solving the some concept related problems. Okay. So here we have our first question. So they are asking us to mark the correct statement. So they have given first statement. The first statement is the critical result shear stress is temperature dependent. Second one is pulse Nabarro stress is temperature dependent. Third one is critical result shear stress and pulse Nabarro stress represent the same quantity. Fourth one, pulse Nabarro stress is theoretical, while the critical shear stress is an experimental quantity. Please try to answer it, guys. So in the quick recapitulation also we have seen what are the similarities and differences between the critical result shear stress and pulse Nabarro stress. You can refer to that and you can easily answer this question. So here, the quick recapitulation. Here we have seen the relation between the critical result shear stress and pulse Nabarro. So both of these represent the minimum stress required to overcome lattice resistance. Means both are representing the same thing. So this option is correct. Okay. Now the critical result shear stress is temperature dependent. So I have already told that the CRSS is find out at the given temperature. So with changing the temperature, the value of CRSS will change. So this option is also correct. Now the pulse Nabarro stress is temperature dependent. So I already mentioned that the pulse Nabarro stress is at the 0 Kelvin. So this can't be our answer. So this is wrong. The last option that we have, pulse Nabarro stress is theoretical, while critical result shear stress is an experimental quantity. This is also true. Okay. Now let's move towards solving second problem. So an FCC single crystal material having critical result shear of 60 megapascal deform under uniaxial tension. What is the tensile stress required to start plastic deformation if the slip plane is 111 and axis of loading is 112? It's very simple question. They have given the critical result shear means they have given the tau r and we have the slip plane, slip direction. Okay. So we have given only slip plane. We need to find out what are the slip direction first. Then we'll use the equation tau r is equal to sigma into cos phi into cos lambda. And we'll find out the value of sigma. So please try to answer this, guys. So for your better understanding, I will draw the figure and then you will try to answer it. Let's say this is my plane, the normal. This is the slip plane, okay? That is 1 1 1. And we have that axis of loading is 1 1 2. Let's say this is our 1 1 2. Let's say this is 5. So we don't know the Burgess slip directions. So we don't know what are the slip directions, and let's say this is my lambda, and on this the tau r is acting. This tau r is equal to 60 MPa. So now try to answer it, guys. We'll be using the equation tau CRSS equal to sigma into cos phi cos lambda. So here the material given is FCC. So in the FCC, the slip plane is of family of 111 and slip direction is 110. So if you need to find out the slip direction for the slip plane 111, then 111 dot product of x, y, z should be 0. So now try all the possible combinations of nation of 1 1 0. So if you do it, you'll get that 1 bar 0 1 comma 1 bar 1 0 and 0 1 bar 1. This will be the slip direction. So now if I write here, that is I need to find out the values of cos phi and cos lambda. So this is loading. This is slip plane, slip direction. This is cos phi, cos lambda, and this is em. Em is nothing but cos phi into cos lambda. So here the loading is given in 112, slip plane is 111, slip direction is 1 bar 0 1. Here also 112, 112. Here also 111, 111, and here we have 1 bar 10 and 0 bar 1. So now find out the values of cos phi, cos lambda and m. So the cos phi or the phi is the angle between normal to the slip plane and the loading axis. So here I have given the loading axis and the normal to the slip plane is given. Now try to figure out the cos phi and cos lambda. So this cos phi comes out to be, that is 112 into 111 divided by both magnitude. So it comes out to be 4 divided by 3 root 2. So as the slip plane and loading direction is not changing, so this is same for everyone. 4 upon 3 root 2. 4 upon 3 root 2. Now the cos lambda, that is the angle between the slip direction and the loading axis. So cos lambda will come out to be, for first case, 1 upon 2 under root 3. Here it will be 0, and here also 1 upon 2 root 3. So now if we find out the value of m, so m will be 2 by 3 root 6 here, 0 here, 2 by 3 root 6. So now which value will you use of m? So the maximum value of m we will use, and the maximum value of m is this. Maximum. So if I use tau CRSS equal to m, I will get the sigma. So sigma equal to tau CRSS is how much? 60 megapascal divided by 2 by 3 root 6. So if we solve, we'll get 90 root 6, or sigma equal to 220.45 megapascal. So this is the answer. So the slip will take place on either of these two slip system, that is 111 and 1 bar 01, or 111 and 1 bar 1. So this is the answer to our second question. Now coming towards our third question. So any doubt in second question, guys? Okay. So here comes the third question. The two parallel and straight screw dislocation lie in a grain of nickel with a grain size about 40 micrometer. If a distance between the dislocation is 1000 Armstrong, and the shear modulus is 30 GPa, and the Burgess vector is 2 Armstrong. So evaluate the total force on each dislocation if the dislocations are on opposite side. Please try to answer it, guys. So let's try to solve it together. So they have given D equal to 40 micrometer or 40 into 10 to the power 6 meter. Similarly, they have given the distance between two dislocations. Okay, so let's say this is my here I have one dislocation, here I have two. Both are parallel to each other, and this is the distance, that is 1000 Armstrong. So this is nothing but the x. So I can write x equal to 1000 Armstrong or 1000 into 10 to the power minus 10 meter. Okay, then we have given the shear modulus. Okay, so that is 30 GPa or 30 into 10 to the power 9 Pascal. So here what I am doing, I am converting all the things in the same unit. Okay, like the grain size was given in the micrometer, so I have converted into the meters. Similarly, distance between the dislocations was given in the Armstrong, so I converted into the meter. So please make sure the all units should be in the same system. So G, and we have here B equal to 2 Armstrong equal to 2 into 10 to the power minus 10 meter. So now we have given two parallel and screw dislocation. So in the dislocation interaction we have seen that the force on dislocation is given by F is equal to plus or minus GB square upon 2 pi into x upon x square plus y square. Is it not? So here in this case, both the cases, they have not given the Burgess vector differently. So I am assuming both the Burgess vector are same for both the dislocation. So GB square upon 2 pi x upon x square plus y square. So as these are parallel and straight, so y equal to 0, and here they are of opposite sign. So opposite sign means negative. So F equal to negative GB square upon 2 pi into y is 0 x upon x square, it is 1 by x. So now you have all the values, find out the force. So F equal to minus G is 30 into 10 to the power 9 into GB square is 2 into 10 to the power minus 10 whole square upon 2 into pi into 1 upon 1000 into 10 to the power minus 10. So here this gets cancelled out. So these 3 will here be 6. So the F will be, so F equal to 1.91 into 10 to the power minus 3 Newton per meter. So 1.91 into 10 to the power minus 3 Newton meter force is coming. So they are asking us the total force on each dislocation. So the total will be this is Newton per meter. So if we multiply with the grain size, we'll get our total force. So F total is equal to 1.91. So this is minus 1.91 into 10 to the power minus 3 into 40 into 10 to the power minus 6 so this F total comes out to be minus 7.64 into 10 to the power minus 7 Newton. So this is the total force on each dislocation if the dislocations are on opposite sign. Okay. So this was our third question. So any doubt in this question, guys? Okay. So no doubt. So let's move ahead. So here comes the fourth question. So a cylindrical rod having diameter 150 nanometer and shear modulus is 200 GPa with a Poisson's ratio of 0.5 and magnitude of Berger vector is 3 angstrom. Find out the shell thickness up to which there is no dislocation for lattice resistance of 1.5 Newton per meter. So you need to find out at what thickness T there will be a no dislocations present in the material, or it is the dislocation free. So the similar type of problem we have sir has covered in the weekly content. So the same problem, nothing change, not a single thing. You can find out the thickness. Please try to solve it. So here also we need to use the concept of image force as the thickness will be very small. Okay, near to the surface only the dislocations will move out, or there will be the no dislocation will be present near to the surface. Okay, so you need to use the concept of image force here. Please try to find the answer, guys. So I'll also solve it with you. So let's say this is the cylindrical rod. Okay. So they are asking at up and with it, this is the diameter of 150 nanometer. They are asking what is the thickness of this dislocation free layer. So if I project it here, so they are asking us to find out this thickness. Okay, so now if we use the concept of image force, okay, so let's say here is one dislocation, okay, at a thickness t, and here at also the with opposite dislocation at a distance t. So first we'll write the given data, that is d is given, diameter is 150 into 10 to the power minus 9 meter, shear modulus is given, that is 200 GPa, that is 200 into 10 to the power 9 Pascal, with Poisson's ratio of 0.5, and magnitude of Burgers vector B is 3 angstrom, that is 3 into 10 to the power minus 10 meter. And they are asking us to find out the T, and they have given the force per unit length is 1.5 Newton per meter. So now if we apply the concept of image force here, so here let's say, so what we'll get, so I will write down the hint. I use concept of image force. So what we'll get, F equal to minus GB square upon 4 pi 1 minus mu into 1 by x. Instead of x, it is t. Is it not? So here we have all the values. So just put the value and get the answer for t. So f is 1.5. So sorry, t equal minus g is 200 into 10 to the power 9 into b square is 3 into 10 to the power minus 10 whole square divided by 4 pi into 1 minus 0.5 into f. F is 1.5. So we'll get t equal to 1.91 into 10 to the power 9 meter, or t equal to 1.91 meter nanometer. So this, up to this much thickness, the material will be dislocation free. So okay, so this was the first question. So any doubt in this question, guys? Okay, let's move to the next question. So here they have asked us to mark the correct statement. That is, the dislocation near the surface only experience the image force. If the image force is greater than the lattice resistance, then dislocation near the surface move towards the free surface spontaneously. Only screw dislocation near the surface experience image force. Both the screw as well as edge dislocation near the surface experience image force. So they are asking us to mark the correct statement. Let's try to answer it, guys. Please try to answer it. So, as in the quick recapitulation, we have already discussed that the dislocation near the surface will try to move out. Okay, will try to come out. So there will be some forces acting. So that is nothing but the image force. So this option is also correct. So first option is correct. So now, when does this dislocation near the surface will come out? Only if the exerting image force is greater than its lattice resistance. So what they have said, if the image force is greater than lattice resistance, then dislocation near the surface move towards the free surface spontaneously. This is also correct. Sorry, guys. Now they have said only screw dislocation near the surface experience image force. So this is not true. It can be either screw or edge. Both will experience the image force near the surface. So this option is not correct. And this final one will be the correct, because both the screw as well as edge dislocation near the surface experience image force. Okay. So moving towards next question. It's very interesting question. So they have given a single crystal of copper is loaded under a state stress such that sigma 2 equal to minus sigma 1, sigma 3 equal to tau 2 3 equal to tau 3 1 equal to tau 1 2 equal to 0. And here 1 equal to 1 0 0, 2 equal to 0 1 0, and 3 equal to 0 0 1. When the stress is sigma 1 equal to 6 kPa, what is the shear stress tau on the first 1 bar slip system, 1 bar 0 slip system, and 1 bar slip system? This is the part A of the question, and the part B is on which of these systems would you expect sleep to first occur as the applied stresses increase? So it's very interesting question. You just need to think a little bit, and you will get the answer. Let's try to answer it, guys. So I'll give you the hint. So here 1, 2, 3, that is given the 100, 2010, 3001. So these are the loading directions are given. So now you have the loading directions, normal to the plane and slip direction. So you can find out the phi and lambda. And if you find out the phi and lambda, sigma is given. So sigma cos phi into cos lambda, you will get the shear stress. So I have given you the hint. Now just try to solve it. So here, what they have given, sigma 2 equal to minus sigma 1, sigma 3 equal to tau 2 3 equal to tau 3 1 equal to tau 1 2 equal to 0. That is the 2D state of stress. And they have given the loading direction. That is one is, this is 1 1, sorry, 1 0 0. The second loading direction is 0 1 0, and third loading direction is 0 0 1. Now so yes, this is the multiple state of stress. We can see that the sigma 1 will give the some shear stress, result shear stress tau r1, and similarly the sigma 2 will also resolve some give some means produce some result stress, that is tau 2. So total will be the total shear stress will be the sum of these two. So let me write down. as it is subjected to two directional loading. So each loading will give corresponding tau r, and the total tau r will be summation of this. So the tau r total will be the summation of this all this. So sigma 1 will produce sigma 1 into cos phi 1 cos lambda 1 plus sigma 2 into cos phi 2 into cos lambda 2. So they have given sigma 1 equal to minus sigma 1. So sigma 1 equal to cos phi 1 cos lambda 1 minus cos phi 2 into cos lambda 2. So here, if you compare it with the original equation, this is nothing but similar to that of our m dash, that is m1 minus m2, and this is our sigma. So you just need to find out the what is cos phi 1, cos lambda 1, cos phi 2, cos lambda 2, and you will get the answer. So I'll write down for first system. So the first system is 1 1 1 slip plane and 1 bar 0 1 bar, and loading in 1 0 0 and 0 1 0. So you need to find out the value of cos phi 1. Similarly, cos phi 2. Similarly here, cos lambda 1 and cos lambda 2. So here you will get m1, here m2, and here you get m equal to m1 minus m2. So now please find out the values and tell me the answer. Any guesses, guys? So first, this is angle between these two, and so angle between these two, cos phi 1, that is here it comes out to be 1 upon root 3 into root 1. Now we need angle between this one and these two. So here also 1 upon root 3 into root 1. Okay. Now we need to find out the cos lambda 1. That is between this one and this one. So it comes out to be 1 upon root 2 into root 1. Similarly, the lambda 2 will be the angle between this one and this one. So it comes out to be how much? 0, 1, 0 and 0, 0, 1 bar 0. So it it is 0 here. So now what is m1 is cos phi 1 into cos lambda 1. So it comes out to be 1 upon root 6, that is root 2 into root 3. Similarly, m2 is 0. So here m1 minus m2, that is 1 by root 6 minus 0. So m dash equal to 1 by root 6. So we have tau equal to sigma 1 upon m dash. So sigma 1 we have 6 kilopascal and m1 we have 1 by sorry guys, I made a mistake here. So here we have tau is equal to sigma 1 into m dash. So here sigma we have 6 Pascal and here we have, that is 1 by root 6. So tau is equal to root 6 kilopascal. So this is the answer for first part of the question A. Now similarly try to find it for the second question, second part, that is the slip plane is 1, 1, 1 and slip direction is 1, 1 bar 0 and loading in 1, 0, 0 and 0, 1, 0. You need to find out cos phi 1, cos phi 2, cos lambda 1, cos lambda 2. So this will give you the m1 and m2. Now you have m1 is m dash equal to m1 minus m2. So you have tau equal to sigma 1 into m dash. So this will give you the answer. First, you need to find out the angle between this one and this one. That will give you the phi 1. So here we'll get 1 upon root 3 into root 1. Similarly, the angle between this one and this one. So you'll get 1 upon root 3 into root 1. Is it not? Now you need to find out the angle between this one and this one. So that is the cos lambda 1. So cos lambda 1 comes out to be 1 upon root 2 into root 1. Okay. Now you need to find out the answer angle between this one and this one. So it comes out to be minus 1 upon root 2 into root 1. Okay. So for your better understanding, I have used the color coding here. Okay. So that blue means here it will represent the value of cos phi 1. That is orange will give you the cos phi 2 multiplication, means the angle between the two vectors. Similarly, the black will give the angle between 101 bar and 110. Similarly, green will give you the angle between 101 bar and 010. So M1 we have how much? M1 we have 1 by root 6 and M2 we have minus 1 by root 6. So here if we put 1 by root 6 minus 1 by root 6. So we'll get M1 dash as 2 by root 6. So here 6 into 2 by root 6. So we'll get 2 root 6. The answer for second part of the question. Now, if you move towards the third part, so they have given one plane and 011 bar direction, slip direction and loading in 100 and 010. Here also you need to find out the cos phi 1, cos phi 2, cos lambda 1, cos lambda 2. So this will give you the M1 and M2. Now you know M dash is equal to M1 minus M2. So now try to figure it out. Again, here angle between this one and this one, it will be 1 upon root 3 into root 1. Now the angle between 111 and 010. So it will be again, sorry guys. So it will be again, sorry. It will be again 1 upon root 3 into root 1. Now we need to find out the angle between this one and this one. That is the cos lambda 1. So here we have cos lambda 1 as 0. Now we need to find out the angle between 011 bar and 010. So here it comes out to be 1 upon root 2 into root 1. So we'll get M1 as 0 and M2 as 1 by 1 by root 6. So here if we write 0 minus 1 by root 6, it comes out to be minus 1 upon root 6. So tau is equal to sigma 1 into m dash. So this will give 6 into minus 1 upon root 6. This will give tau is equal to minus root 6 kilopascal. So all the units are in kilopascal. Okay. So this is the answer to a third part of the question. Now here comes the second part of the question, that is B. So on which of this system would you expect slip to first occur as the applied stress is increased? So slips will occur. So as all these three, the sigma 1 is common. So if the slip needs to be occur on any surface, system, any of this given system, so the value of m should be highest. So if we compare, here we have 1 by root 2, 1 by root 6, here 2 by root 6, and at the third, that is minus 1 upon root 6. So for this case, the m is maximum, that is m dash is maximum. So since m dash is highest for 1 1 1 and 1 1 bar 0 system, slip system, so slip will occur first on this. Okay, so this was just the easy question. So if you have any doubt in this question, you can ask, or you can take a careful look at this question, how we have solved it. So, okay. So now here comes the today's session's last question. So the question is like that: evaluate the force per unit length in case of two parallel edge dislocation of opposite sign lies on same plane having Poisson's ratio 0.3, shear modulus 40 GPa, and magnitude of Burgess vector is 3 angstrom, and distance between dislocation is 1200 angstrom. So they are asking us to find out the force per unit length. Please try to answer it, guys. It's very simple. The similar question we did earlier. I think that was the question number 3, where the dislocations were screw. Now here we have the edge dislocation. So here in this question they have given the values, that is force per unit length in case of two parallel edge dislocation. So Poisson's ratio nu is given, that is 0.3. Shear modulus is given, that is 40 GPa or 40 into 10 to the power 9 Pascal. Berger's vector is given, that is 3 angstrom or 3 into 10 to the power minus 10 meter, and the distance between two dislocation is 1200. So let's say this is my two dislocations. Okay, so now here they are lying on the same plane. So this is the same plane of opposite sign. Sorry guys, I made a mistake here. So that too of opposite sign. So this of opposite sign, and distance between them is nothing but 12,000 Armstrong. So this is the value of x. So x equal to 1,200 Armstrong or 1,200 into 10 to the power minus 10 meter. So here in this case, in case of edge dislocation, we know the Fx equal to plus minus GB square upon, okay, sorry, I will write it here so you will not get confused. So force on dislocation is plus minus GB square upon 2 pi 1 minus nu into x upon x square minus y square divided by x square plus y square whole square. So here they have the two parallel edge dislocation of opposite sign. So this will give us the negative. And the second thing, that is they have given lies on the same plane, means y equal to 0. So if you put y equal to 0 in this equation, we will get fx equal to plus minus gb square 2 pi 1 minus nu into this y is 0, 0. So and this one gets cancelled out, and we will remain with the 1 by x. So now we have all the values, just put it. So fx equal to minus g is 40 into 10 to the power 9 into b is 3 into 10 to the power minus 10 whole square divided by 2 into pi into 1 minus mu 1 minus 0.3 into 1 by x is 1200 into 10 to the power minus 10. So if you calculate it, you will get fx somewhere around 6.82 into 10 to the power minus 3 Newton per meter. So this is the answer. So this was the last question for today's session. So do you have any doubt till now? Just ask. Otherwise, we'll end our session here itself. So I think no doubts are here. So thank you very much for attending, and let's end our session here. Okay. Thank you guys.